It's the most powerful technology of our time. But how does artificial intelligence actually work? We're pulling back the curtain. This is AI Deconstructed.
In our last episode, we explored the fascinating world of reinforcement learning. We learned about agents, environments, states, and actions, and the central idea of learning through trial and error, guided by a reward signal. We saw how an algorithm like Q-learning could build a cheat sheet, a Q-table, that tells an agent the expected future reward for any action in any state, allowing it to navigate its world and maximize its cumulative reward. This paradigm, this idea of learning from treats and punishments, rounded out our trifecta of machine learning approaches, alongside supervised learning from Episode 8 and unsupervised learning from Episode 9. These three paradigms, supervised, unsupervised, and reinforcement, tell us what the learning objective is. Are we learning from labeled examples? Are we finding hidden structures in unlabeled data? Or are we learning a policy from rewards? But this framework doesn't always specify the engine that does the learning. In our discussion of supervised learning, for instance, we've hinted at models like decision trees or linear regression. But for the past several decades, one particular kind of engine has come to dominate the field, an engine so powerful it has unlocked capabilities that were once pure science fiction. This engine is inspired by the most complex and powerful learning machine we know, the human brain. And so, today we begin Part 4 of our curriculum, diving deep into neural networks. We are going under the hood of deep learning itself, but we don't start with the massive billion-parameter models that power today's generative AI. We start, as any good curriculum must at the very beginning. We start with the atom from which all this complexity is built. We start with the ancestor of every modern neural network. Think for a moment about the profound mystery locked inside your own skull. Billions of simple, individual cells, neurons, are firing in a complex, silent symphony. Together, they produce everything you are, your thoughts, your memories, your ability to recognize a friend's face or compose a piece of music. For the pioneers of computing, this was the ultimate inspiration. If nature could build such breathtaking intelligence from simple, repeating units, could we do the same? Could we forge a thinking machine from a single artificial brain-like component? Today, we meet the first real answer to that question. It wasn't just a model that could compute, but one that could learn. We are talking about the Perceptron. Our journey will take us from the source code of intelligence, the biological neuron, to its first digital ghost, the brilliant but static McCulloch-Pitts neuron of 1943. Then we will witness the birth of machine learning with Frank Rosenblatt's revolutionary 1958 Perceptron, a device that could adapt through experience. And finally, we will confront the fundamental wall it hit, a simple puzzle called the XOR problem, and understand why this apparent failure was actually the crucial signpost pointing toward the future of all artificial intelligence. Before we can build an artificial neuron, we have to understand the original. A biological neuron is a masterpiece of information processing. Imagine it as a tiny, organic computer. It has input antennas, called dendrites, which receive thousands of electrochemical signals from neighboring neurons. These signals flow into the soma, or the cell body, which acts as a central processor. The soma's job is to integrate or sum up all of these incoming signals. But here is the critical part. The soma doesn't just add signals passively. It operates on an all-or-nothing principle. It waits for the combined strength of the incoming signals to cross a specific firing threshold. If, and only if, that threshold is crossed, the neuron fires. It sends its own powerful signal down its output cable, the axon, to communicate with other neurons. The connection points where these signals are transmitted are called synapses, and they have varying strengths. A strong synaptic connection means a signal from one neuron has a greater impact on the next. A weak or inhibitory connection means it has little or no impact, or even a negative one. This concept of connection strength is the direct biological inspiration for the mathematical weights that are the cornerstone of all artificial neural networks. In 1943, long before silicon chips dominated the world, two researchers from different fields came together to create the first mathematical model of a neuron. Warren McCulloch was a neuroscientist, and Walter Pitts was a logician. Their collaboration was not born from computer science, which barely existed, but from the deliberate fusion of neuroscience and mathematical logic. Their goal, outlined in their seminal paper, A Logical Calculus of Ideas Immanent in Nervous Activity, was to see if the mechanics of the brain could be explained with the rigor of formal logic. The result was the McCulloch-Pitts neuron, or MCP neuron. It was a radical simplification of its biological counterpart, designed to capture the essence of its function in the language of mathematics. Here's how it worked. First, it used binary inputs and outputs. The MCP neuron was a digital device. It only understood binary signals, 1 for active or firing, and 0 for inactive. Second, it performed a simple summation. It took all of its binary inputs and performed a simple sum. This aggregation was called the function g. Third, it had a fixed threshold. The decision to fire was governed by a second function, f. This function compared the sum from g to a predefined fixed threshold, which we'll call theta. If the sum was greater than or equal to theta, the neuron fired and output a 1. Otherwise, it remained silent, outputting as 0. The true power of this model, and its lasting significance, was not in its biological accuracy but in its philosophical implications. It was the first formal demonstration that a brain-like structure could perform logical computation. It lent mathematical weight to the idea that thought itself might be a form of computation, a concept that had been explored abstractly by thinkers like Alan Turing. The MCP neuron was a proof of concept that the mind could be understood as an information processing machine. The most stunning demonstration of the MCP neuron's power was its ability to act as a basic logic gate, the fundamental building block of all digital computers. Let's see how. Imagine an MCP neuron with two inputs. To create an AND gate, we simply set the threshold theta to 2. The neuron will only fire if input $1 and input 2 are both 1, because only then will their sum, 1 plus 1 equals 2, be equal to or greater than the threshold. Any other combination, 0 and 0, 1 and 0, or 0 and 1, results in a sum less than 2, so the output is 0. To create an OR gate, we set the threshold theta to 1. Now, the neuron fires if input $1 or input 2 or both are 1. The sum will be 1 or 2, which meets the threshold. Only the input 0 and 0 fails to fire. This was a revelation. A single, simple model of a brain cell could replicate the foundations of computational logic. However, the MCP neuron had a critical, defining limitation. The connection strengths, the weights, were all fixed at 1, and the threshold theta had to be manually set by the designer for each specific problem. The MCP neuron could compute, but it could not learn. It was a static calculator, not an adaptive learner. For the next great leap, AI would need to evolve. This brings us to a common misconception. People often equate the McCulloch-Pitts neuron with the perceptron. But the key difference, the revolutionary leap, was the introduction of learning. The MCP neuron was a fixed model. The perceptron was an algorithm that could find the right parameters on its own. Fast forward to 1958. The Cold War was escalating, and the world was entering the age of massive, room-sized computers like the IBM 700-4. At Cornell Aeronautical Laboratory, a research psychologist named Frank Rosenblatt was captivated by a different problem. His goal wasn't just to model logic, but to understand and replicate the brain's mysterious ability to perceive, recognize, and, most importantly, learn from the world around it. This shift in focus from the domain of pure logic to the domain of psychology and learning was profound. Rosenblatt's seminal 1958 paper was not published in an engineering journal, but in Psychological Review, and it was titled The Perceptron, a probabilistic model for information storage and organization in the brain. He wasn't just building a better calculator, he was trying to model a fundamentally different aspect of cognition, adaptation. In July 1958, the U.S. Office of Naval Research held a press conference to unveil Rosenblatt's creation, the Mark I Perceptron. The reaction was electric. The New York Times reported on the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. Rosenblatt himself claimed it was the first machine which is capable of having an original idea. This was possible because the Mark I Perceptron wasn't just an algorithm, it was a physical machine. It had an input retina made of 400 photocells and a tangled web of wires, and it could physically learn to distinguish patterns, like telling the difference between cards marked on the left and cards marked on the right. This tangible reality made the abstract idea of AI concrete and thrilling. It also created a powerful public narrative about electronic brains, setting a cycle of breakthrough, hype, and controversy that would define AI for decades to come. So what made the perceptron so revolutionary? It took the core idea of the MCP neuron and added crucial upgrades that unlocked the ability to learn. The first and most central innovation was weighted inputs. In the MCP neuron, all inputs were treated equally. The perceptron, however, assigned a numerical weight to each input connection. Think of a weight as a measure of importance. A large positive weight means that this input is strong evidence for firing. A large negative weight means it's strong evidence against firing. The key insight was that these weights were not fixed, they could be adjusted. Learning, in the world of the perceptron, is the process of finding the right weights. The second key upgrade was the bias term. The perceptron also added another adjustable parameter called the bias. You can think of the bias as the neuron's baseline predisposition to fire, independent of any input. A high positive bias makes the neuron eager to fire, requiring less stimulation from the inputs. A high negative bias makes it reluctant, requiring a very strong input signal. This gave the model more flexibility. With these two additions, adjustable weights and a bias, the stage was set. The neuron was no longer a static logic gate, it was a dynamic device capable of changing its own internal parameters based on experience. So, let's deconstruct this. How does it actually work? We are going to build one, conceptually, from the ground up. Let's use a simple, concrete example. Let's say we want to build a perceptron that decides whether a student will pass or fail a test. This is a binary classification problem, which we discussed in episode 8. The output should be 1 for pass and 0 for fail. What is the evidence? These are our inputs. Let's pick 2. First input zone will be hours studied. Second input x2 will be hours slept the night before. These inputs are the features of our data point, For one student, the inputs might be zone equals 8 hours and x2 equals 7 hours. For another, zone equals 2 hours and x2 equals 4 hours. Now, what about the importance of this evidence? This is where the weights come in. The weights, 1 and WTWO, are the parameters that our perceptron will learn. They represent how much each input contributes to the final decision. Let's just start by picking some random weights. This is how training almost always begins. Let's say the weight for hours studied, 1, is 0.3. The weight for hours slept, WTWO, is 0.1. These weights represent our model's current uninformed belief about the problem. The next step is the summation. Just like the cell body in a neuron, the perceptron calculates a weighted sum of its inputs. The formula is simple. You multiply each input by its weight and add them all together. The sum equals zone times 1, added to x2 times WTWO. Let's take our first student who studied for 8 hours. So zone equals 8 and slept for 7 hours. So x2 equals 7. The weighted sum is 8 times 0.3 plus 7 times 0.1. This equals 2.4 plus 0.7, which gives us a total evidence score of 3.1. Now the final step, the activation function. The perceptron takes this score, 3.1, and decides whether to fire, output 1 or not, output 0. To do this, it compares the sum to a threshold, just like the MCP neuron. Let's randomly pick a threshold, say 4.0. Our rule is, if the sum is greater than the threshold, output 1. Otherwise, output 0. In our case, the sum 3.1 is not greater than the threshold 4.0. So the perceptron outputs 0. It predicts fail. This is the entire forward pass of a perceptron. It takes inputs, multiplies them by weights, adds them up, and compares the sum to a threshold. Now, before we get to learning, there's a clever mathematical trick that makes life much easier. This idea of a separate threshold is a bit clumsy. Instead of saying, is sum greater than threshold, we can just subtract the threshold from both sides of the inequality. The new question becomes, is sum minus threshold greater than 0? This doesn't change the answer, right? If sum was 3.1 and threshold was 4.0, sum minus threshold is negative 0.9, which is not greater than 0. Same result. But look at what we just did. We've combined everything into one single sum. We have zone times 1 plus x2 times WTWO minus threshold. Mathematicians just gave that negative threshold term a new name. They called it the bias. It's written as B. So bias equals negative threshold. In our case, the bias B would be negative 4.0. Our new formula for the weighted sum, which we'll now call Z, is Z equals zone times 1 plus x2 times WTWO plus B, and our new activation function is much simpler. If Z is greater than 0, output 1, otherwise output 0. This type of activation function is called a step function or a heaviside step function. It just steps from 0 to 1 right at the 0 mark. This bias term is incredibly important. You can think of it as another weight, W0, whose corresponding input, x0, is always 1. The bias represents the neuron's baseline tendency to fire, even if all other inputs are 0. A high positive bias means the neuron is trigger-happy and wants to fire a 1. A high negative bias means the neuron is very reluctant and will need a lot of positive evidence from its inputs before it fires. So our full model is, first, the inputs, zone and x2. Second, the parameters 1, WTWO and B. Third, the weighted sum, where Z equals 1 times zone plus WTWO times x2 plus B. And fourth, the prediction, output 1 if Z is greater than 0, and output 0 if Z is less than or equal to 0. This is the anatomy of a perceptron. Now for Rosenblatt's masterpiece, the learning rule. How do we find the right values for 1, WTWO, and B? We need a dataset. This is supervised learning, which we covered in episode 8. We need a list of past students where we have both the inputs, hours studied and hours slept, and the correct answer, the label. Did they actually pass or fail? Let's call the correct answer Y. So Y equals 1 for pass and Y equals 0 for fail. The genius of the perceptron is that it learns in a very human way. It learns from its mistakes. This principle established a foundational concept in supervised learning. Learning is driven by error. The algorithm is fundamentally reactive. It only changes when it gets something wrong. Let's go back to our first student. Studied 8 hours, slept 7 hours. Our model with its random weights of 1 equals 0.3, WTWO equals 0.1, and B equals negative 4.0, predicted 0 or fail. Now we look at our dataset, and it turns out this student actually passed. The correct label Y is 1. Our model made a mistake. We predicted 0, but the answer was 1. This is a false negative. The model should have fired, but it didn't. How do we fix this? We need to adjust our weights, 1 and WTWO, and our bias B. To make the sum Z larger for this student, we need to push Z up over the 0 threshold. The perceptron learning rule is brilliantly simple. It says, to make the sum larger, add a small fraction of the inputs back to the weights. Let's define a small fraction. We'll call it the learning rate, often written as the Greek letter alpha. This is just a small number, like 0.1, that controls how big our nudge is. We don't want to overcorrect. The update rule for a false negative, where we predicted 0 but Y equals 1, is new weight equals the old weight, plus the learning rate multiplied by the input. Let's update our parameters. Let's update 1. The old one was 0.3. The input zone was 8. The new one equals 0.3 plus the result of 0.1 times 8. That's 0.3 plus 0.8, which equals 1.1. Now for WTWO. The old WTWO was 0.1. The input x2 was 7. The new WTWO equals 0.1 plus the result of 0.1 times 7. That's 0.1 plus 0.7, which equals 0.8. And for the bias B. The old B was negative 4.0. The input for the bias is always 1. The new B equals negative 4.0 plus the result of 0.1 times 1. That's negative 4.0 plus 0.1, which equals negative 3.9. Our model's brain has changed. The new parameters are 1 equals 1.1, WTWO equals 0.8, and B equals negative 3.9. Notice what happened. The inputs that caused the mistake, both zone and x2, were positive. Had their influence increased, the model is now more sensitive to hours studied and hours slept. If we rerun our student where zone equals 8 and x2 equals 7 through this new model, Z equals 8 times 1.1 plus 7 times 0.8 plus negative 3.9. So Z equals 8.8 plus 5.6 minus 3.9, which means Z equals 10.5. 10.5 is greater than 0, so the new prediction is 1 or pass. We fixed the mistake for this one example. Now what about the other kind of mistake? Let's take a new student. Student 2. Studied 2 hours, so zone equals 2, and slept 4 hours, so x2 equals 4. The correct answer from our dataset Y is 0 or fail. Let's see what our new model with 1 equals 1.1, WTWO equals 0.8, and B equals negative 3.9 predicts. Z equals 2 times 1.1 plus 4 times 0.8 plus negative 3.9. So Z equals 2.2 plus 3.2 minus 3.9, which means Z equals 1.5. 1.5 is greater than 0, so our model predicts 1 or pass. Error, we predicted 1 but the answer was 0. This is a false positive. The model fired when it shouldn't have. How do we fix this? We need to make the sum z smaller. We need to push it down below the 0 threshold. The Perceptron learning rule for a false positive, where we predicted 1 but y equals 0, is new weight equals the old weight minus the learning rate multiplied by the input. We subtract a fraction of the inputs from the weights. Let's update our parameters again. Let's update 1. The old one was 1.1. The input zone was 2. The new one equals 1.1 minus the result of 0.1 times 2. That's 1.1 minus 0.2, which equals 0.9. Now for WTWO. The old WTWO was 0.8. The input x2 was 4. The new WTWO equals 0.8 minus the result of 0.1 times 4. That's 0.8 minus 0.4, which equals 0.4. And for the bias B, the old B was negative 3.9. The input is 1. The new B equals negative 3.9 minus the result of 0.1 times 1. That's negative 3.9 minus 0.1, which equals negative 4.0. The weights have changed again. The model is now 1 equals 0.9, WTWO equals 0.4, and B equals negative 4.0. It has become less sensitive to hours studied and hours slept, and its bias has become more negative, making it more reluctant to fire. And what if the prediction is correct? If we predict 1 and y equals 1, or we predict 0 and y equals 0, the rule is simple. Do nothing. Don't fix what isn't broken. This entire process is training. You show the Perceptron one example from your training data. You make a prediction. You compare the prediction to the true label. If they match, you do nothing. If they don't match, you nudge the weights and the bias in the direction that makes the correct answer more likely. Then you move to the next example, and the next. You loop through your entire dataset over and over, one example at a time. Each full pass through the dataset is called an epoch, and with each mistake, the weights get a tiny bit better. This intuitive process is formalized in the elegant Perceptron learning rule. When the Perceptron makes a mistake, it updates each of its weights according to a simple formula. We can express this update in one single equation. The new weight equals the old weight plus the learning rate times the quantity of target minus prediction, all times the input. Let's break that down. The term target minus prediction is the error. Here, target is the expected or correct output, RY 1 or 0, and prediction is the output from the Perceptron 1 or 0. If the prediction is correct, the target and prediction are equal. The error is 0 and the weight doesn't change at all. This is the mathematical equivalent of do nothing if you are right. If we have a false negative, where the target is 1 and the prediction is 0, the error is 1 minus 0, which equals positive 1. The update is positive, so we add a fraction of the input to the weight. If we have a false positive, where the target is 0 and the prediction is 1, the error is 0 minus 1, which equals negative 1. The update is negative, so we subtract a fraction of the input from the weight. This single rule covers all cases. The learning rate, that alpha value, is one of the very first examples of a hyperparameter in machine learning. It's a setting that isn't learned by the model itself, but must be chosen by the practitioner. This foreshadows a central challenge in all of modern AI, the art and science of hyperparameter tuning, finding the optimal settings to guide the learning process itself. For a time, the Perceptron seemed unstoppable. Rosenblatt was able to prove a theorem, the Perceptron convergence theorem. It states that if a dataset is linearly separable, the Perceptron learning algorithm is guaranteed to find a set of weights that separates it in a finite number of steps. But what does linearly separable mean? This brings us to what the perceptron is actually doing, geometrically. Our model is, predict 1 if 1 times zone plus WTWO times x2 plus b is greater than 0. That expression, 1 times zone plus WTWO times x2 plus b equals 0, is the equation of a line. If you have two inputs, zone and x2, you can plot your data on a 2D graph. Hours studied is the z-axis, hours slept is the y-axis. Every student is a dot on this graph. We can color the dots that passed blue and the dots that failed red. All the perceptron is doing, all that this training process is finding a single straight line that separates the blue dots from the red dots. That's it. That's all it can do. All the points on one side of the line will result in a sum greater than 0, predicting pass. All the points on the other side will result in a sum less than or equal to 0, predicting fail. The weights 1 and WTWO control the slope of the line. The bias B controls the intercept, where the line crosses the axis. The learning algorithm is just wiggling this line around, epoch by epoch, until it finds one that gets all the training examples on the correct side. This property is called linear separability. A perceptron can only solve problems where the two classes can be perfectly separated by a single straight line. If you have 3 inputs, it's not a line. It's a flat plane in 3D space. If you have 100 inputs, it's a hyperplane in 100-dimensional space. But the concept is the same. It's a single, flat, linear boundary. This leads to a common misconception. People often assume that the perceptron finds the best possible line to separate the data, perhaps the one that leaves the most room or margin on either side. It does not. The perceptron convergence theorem is an amazing guarantee, but it only guarantees that the algorithm will find a line, any line, that works. It's perfectly happy with a line that just barely scrapes by the data points. This is a key difference from other linear classifiers, like support vector machines, which are explicitly designed to find the optimal boundary with the maximum margin. The perceptron is simpler. It just finds the first solution that gets the job done. And for many simple problems, that's enough. Let's go back to our logic gates. Can a perceptron learn the dollar and dollar function? Let's plot it. Input zone on the z-axis, x2 on the y-axis. The point 0, 0 gives output 0. The point 1, 0 gives output 0. The point 0, 1 gives output 0. The point 1, 1 gives output 1. Can you draw one straight line to separate the one true point at 1, 1 from the 3 false points? Absolutely. A line running diagonally between 0, 1 and 1, 0 will do it perfectly. A perceptron can learn in. Can a perceptron learn the $OR function? The point 0, 0 gives output 0. The point 1, 0 gives output 1. The point 0, 1 gives output 1. The point 1, 1 gives output 1. Can you draw one line to separate the one false point at 0, 0 from the 3 true points? Easy. A diagonal line near the origin does it. A perceptron can learn OR. This is what linearly separable means. But what happens when a problem isn't so simple? Enter the perceptron's nemesis, the $XOR dollar, or exclusive $OR function. $XOR outputs a 1 only if the two inputs are different. It means one or the other, but not both. Let's look at its truth table. Input zone is 0, input x2 is 0, output is 0. Input zone is 0, input x2 is 1, output is 1. Input zone is 1, input x2 is 0, output is 1. Input zone is 1, input x2 is 1, output is 0. Now try to visualize these 4 points on a graph. The points 0, 1 and 1, 0 belong to the 1 class. The points 0, 0 and 1, 1 belong to the 0 class. Now, try to draw a single straight line that can keep the 2 1s on one side and the 2 0s on the other. You can't. It is geometrically impossible. No matter where you draw the line, you will always have at least one point on the wrong side. This is the definition of a nonlinearly separable problem. The dollar XOR dollar problem is more than just a clever puzzle. It's a simple, elegant metaphor for real-world complexity. Many problems in the world do not have simple, linear answers. I like movies that are short and funny, or long and serious, but not short and serious or long and funny. That's a dollar XOR dollar problem. You can't separate that preference with a single linear boundary. The dollar XOR dollar problem proved, in the simplest possible terms, that a single neuron was not powerful enough to capture this kind of complexity. This limitation was famously and rigorously analyzed in the 1969 book Perceptrons by AI pioneers Marvin Minsky and Seymour Papert. Their work was a mathematical bombshell. It proved that the single-layer perceptron was fundamentally incapable of solving non-linearly separable problems. While mathematically correct, their critique was interpreted by many in the research community and, crucially, by funding agencies as a devastating indictment of the entire neural network approach. This, combined with the earlier overblown hype from 1958, contributed significantly to a period of reduced funding and interest in AI, a period now known as the first AI winter. But this is a powerful lesson in how science truly advances. The failure of the perceptron was not a failure of the scientific method, it was a triumph. It precisely and rigorously defined the boundaries of a model's capabilities. Progress in science rarely comes from a model's successes, but from a deep understanding of its most profound limitations. The dollar XOR dollar problem proved that a single neuron was not enough. The solution wasn't to abandon the idea, but to ask the next logical question. What happens if we start connecting them together, like the brain does? The perceptron, simple as it may seem today, is a giant in the history of artificial intelligence. Though it couldn't solve every problem, it introduced the foundational concepts that are the absolute bedrock of all modern deep learning. It gave us the idea of an artificial neuron with adjustable, weighted inputs and a bias, and it established the core principle of learning by iteratively adjusting those weights based on error, using a learning rate. Every complex neural network in the world today, from the one in your phone that recognizes your face, to the massive models that power ChatGPT, is a direct descendant of this idea. They are all, at their core, vast networks of simple processing units, adjusting their internal connections based on feedback to get progressively better at their task. They are all built upon the simple, elegant, and world-changing principles first demonstrated by Frank Rosenblatt's perceptron. We have met the simple brain cell. Now we must build the brain. We must see what happens when we connect layers of these perceptrons, allowing them to draw not just lines, but complex, curving shapes. This is the key to conquering the dollar XOR dollar problem and opening the door to learning the true, nonlinear complexity of our world.
You've been listening to AI Deconstructed. Join us next time as we unpack another layer of the technology shaping our future. Until then, stay curious. Subscribe for more.